Okay, well, let's just go ahead and go, and we'll hope that maybe Fry will figure out what his problem is and he will be able to join. But a lot has been going on over the last week, last month rather, since our last meeting, and I wanted to catch everybody up on it. And some of these are software related, and some are that I put out a YouTube video, and I hope, raise your hand if you've seen it. Okay, well, we got a quorum. Okay, well, that is actually doing very well. And of course, how well a video does is very much dependent on the thumbnail and the title rather than the content, because when you count clicks, people click before they see any of the content. So, but it is also getting a lot of view time. So people who get on it are actually spending a lot of time. And what I wanted to do is to run a quick review this morning of the overall brain simulator, what it does, and then we'll, one moment. Yeah, Fry says he's going to try to run the app. And so we have going to talk about the brain simulator structure for about 2 minutes or 5 minutes, and then I'll go back to the demonstration of how the UKS runs, and I'll show a couple of different things that I haven't talked about before. And then we'll talk about the agents. And to understand what agents are about, I need to first give the overview of what that means and what it's good for. And so I have a couple of slides that are useful, and let's see if we can show them here. There, share, there. Okay, so the brain simulator has two real parts: the universal knowledge store, and then it has a selection of agents. And the reason I want to emphasize this today is when we get to the meat of new stuff, it's all about the agents. Some of the agents can talk to the outside world. So if you have an agent, it could have a sound input or a microphone input, or it could be controlling a robotic body or doing something. But that way, the universal knowledge store, which stores all of the information, is somewhat isolated from the world, but it's all of these agents that do things. And when I say agent, I'm just talking about a piece of software that does something. It doesn't have, essentially, there's no specific requirement, and they can run on timers or they can be independent. But in the brain simulator, one thing that's cool or important to understand is that if you want to have a user interface, you have to have an agent, because agents have related dialog boxes. So if a lot of things are written as agents that maybe shouldn't be, could be written somewhat differently as something else. Universal knowledge store, we'll talk about that, is a graph of nodes and edges, and the nodes are called things and the edges are called relationships, and I'll show all of that in a moment. It supports attribute inheritance with exceptions inherently. So the graph looks something like, I mean, pictorially, you can look at it like this, where we say Fido is a dog, where the relationship actually relates a relationship type and another relationship. So this is a relationship of Fido is a dog, and this is a relationship of Fido has fur. And so for nomenclature, a relationship essentially connects two things, the source and the target, but it has a type, and the type is also a thing. So a relationship connects three things in a more general way of looking at it. We're not going to be talking about clauses today. They're a feature that allows you to relate multiple relationships together, and I'll show you some of the query options. And so some of the relationship agents that we'll be talking about are, and this will all make a lot more sense in about 2 minutes, attribute bubbling and automatic subclassing. I'm working on vision, and one of the things that I expect to have running in the next month or two is going to be the MNIST database of handwritten digits so that we can check that out and see how well it works. And I think that's all I want to say about that until we get to the software. And the software is there. So all 4 of these dialog boxes represent agents. And they happen to be listed here. And you can open a different file and get different numbers of agents. This agent shows the content of the UKS, and it shows it in such a way that you can get an idea of what's going on. And here we've chosen the root of this picture to be mammal, but you can select any root you want. The actual root of the data structure is a thing called thing. So we can go to the outside by thing, and you can see that mammal is buried down here. So we'll go back to mammal. And you can see that it searches pretty rapidly as you're typing. It helps you get to where you're going. So under mammal, the structure of this is to say that a cat is a mammal and Fluffy is a cat. So that's what the indentation means in this instance. Underneath cat, you can also have relationships. So these are things that are relationships of the cat. Down here we have relationships of Fido. So Fido is a dog, and Fido has a collar, although not all dogs have collars, and not all, but we can say in general that all dogs can bark, all dogs have tails, and all dogs have fur. And in the event you run into exceptions, you can handle them as exceptions rather than making them more generic. And here we can say a mammal has fur and a mammal has 2 eyes. And so if I search for Rover, so in this instance, Rover has no given properties. But if I search for the attributes of Rover, Rover can bark, and he has fur, and he has a tail, and he has 2 eyes, even though we've said absolutely nothing about Rover. And if we run this query, we can see where these relationships came from. And these are the confidences in the relationships. So we've got Rover can bark because dogs can bark, and Rover has 2 eyes because mammals have 2 eyes. And so that is all inherited. Is that reasonably clear to all of you?
Charles, first of all, I finally got in, so thanks.
Hey, you're here. Good.
We've you said Rover has no attributes, but Rover does have the relationship of dog.
Yes,
right?
he is a dog, but yes.
So your relationship, you're under relationships for Fido, for example, it's only saying Fido has a collar. It's not saying Fido is a dog, but that's implicit because of the indentation.
Yes, exactly. So, and that's only a figment of the way I wrote this dialog box, because it's easier to see this way.
Yeah. I just wonder whether it might be good to redundantly say under relationships, Fido is a dog. Just to emphasize the fact that is a relationship just like all other relationships. I mean, it's a little bit special, but
and because it inherits and is transitive, the is a relationship in this instance is like the has a relationship. Fry has hands and hands have fingers, therefore Fry has fingers. It's exactly the same process.
Yeah.
inheritance on the has a relationship than it is on the is a relationship.
Uh-huh.
And so if I were to add a relationship, let's here it shows up Bowser is brown, and it is
Yes.
a relationship of Bowser.
Yes.
And here we've searched for Rover. These are the attributes of Rover. We can search for the attributes of Bowser. And they're unique by the case that but Bowser is brown. Interesting tongue twister there. But you can search by the attributes. So I can say, give me all of the things that is brown. And Bowser is the only thing in the data that we've put in so far that is brown. And the way this dialog box works is you put in various things and it adds them to a list. And this list of attributes is ANDed together. So if we say has a tail, now we get many more results, but you can see they have lower confidence. So Bowser is the one that's brown and has a tail. The dog and the cat also have tails, but they have a much lower confidence because they're not brown. And at some point you decide that the confidence below, at say below 60% is non-relevant.
Okay, so type in this dialog box means relationship.
So yes, it's the relationship type.
Okay. Okay, well then say relationship. Can you just say relationship or relationship type instead of just type? That would make it clearer. And then in particular, we can also type in ISA into that dialog box where you now have has, correct?
Yeah, I don't know if that works in this picture, but we could, that actually works here.
Well, you see what I'm trying to do? I'm trying to say that ISA is a relationship just like all these other relationships, and therefore we ought to be able to use it in all the places that we're using relationships.
Yes. So
that's the thrust of my, and I realize that it's redundant in this hierarchy. I don't know, maybe you could put is a relationship under relationships, but put it in italics or something to let the user know that it's really redundant, or I'm not sure what, but just, I want to see the list of all the relationships that this thing has, because when you're creating, this gets back to something I want to talk to you about later on, but when you're first recognizing a new object, you have no idea what it is. You don't know that it is an animal or is a house or anything. And then we're going to develop that as the learning process happens. So is going to be learned just like maybe has fur is learned or inherited.
Exactly. And this relationship is the one that I use when I'm recognizing shapes. So we'll say you don't use this dialog box because the dialog box is clumsy, but you say it has a corner and a distance and a corner and a distance and a corner and a distance. And if it has those attributes, it's a square or it's a triangle or.
And you know me, I'm a hacker. I would love to see the low level somehow represented in this high level dialog box. I mean, that would be very cool to make the connection between all this low level junk and all this high level junk. Well, they're all relationships, and that's really cool.
Yeah. And in some instances, we'll find that things are clumsy specifically so that they can fit that paradigm of being only relationships.
Yeah, which is okay. Okay, now this is relationship, bothers me is brown, because normally I would say, the relationship really has color or something like
Exactly.
that, right? But what does really is mean?
Yeah, well, we want to not get stuck on the distinction between problems of the data structure and problems of the English language. And
yeah.
we could say has color. Now it has that attribute instead. And the problem of doing that is that we'll delete that one, is that when you're searching, you have to know has color. But I've used has attribute, and the way this is intended to work is if I'll say, I want to search for the attributes of Bowser that have an ancestor of being a color. So one would normally say brown is a color.
Yep.
Got my shift lock there. And yeah, that doesn't work on that doesn't work on this side, but it'll work on this side. So is a dog, and I think, well, I haven't done this in such a long time. I've forgot which attribute goes in which place, but the intent is of the filter and of the ancestor.
Yes.
Is to be able to filter the result so it has a parent. So rather than having to specify that Bowser has color brown, we'll invent a word for is, like has attribute. And Bowser has attribute of being brown. And now you want to search for the attributes that are color related, and you'll get his color.
Yeah, it's almost like you could have a search and I say, go 2 or 3 levels out from this node and see if the node is brown. And then we don't have to know if brown is the color of the fur or color of the eyes or not even a color. We just say, search for this value from any relationship. Does this make sense? And then we don't have to specify the relationship at all. We just say any relationship and bound it. We don't want to go over the whole net on our search. Just 2 or 3 levels. Right. You indicate how many you want.
The way that works, by the way, and I haven't talked about this yet today, is that I'm going to show details, and it turns out that every relationship has a confidence level, and as you go from hop to hop through the data structure, the relationship confidences all multiply. So nice. You can see they'll get progressively smaller.
Nice.
And once they get below some threshold, like 50 or 60, you give up.
Perfect.
Exactly.
Yeah, and then you can learn, the human can learn, brown has the relationship to Fido of fur color. And we didn't have to know in advance to search for fur color. And we just said, there is some relationship between brown and Fido. And now I find it through this mechanism, and it tells me, that yes, and that relationship happens to be fur color.
Right. And one of the things you can do is we can say Spot has brown fur. And this is a figment of this dialog box. And what this has done is it's created under the hood, it's created a new thing called fur.brown. And it is a child of fur, but it is brown.
Good.
And we may want, whenever I say is, you think has attribute. And this is how I can search on brown. Because if you don't have a link to something that is brown, you're never going to get there.
Yeah.
And this becomes clumsier in numbers, where I say a dog has 4 legs. And now we got to go back to dog over here. And what has happened is this has created this relationship type, which is has.4, and has.4 has the relationship of is4, and the parent of is has. And the reason it does it this clumsy way is it's the only way to search on for and be able to get a result.
Okay, so we could say, what's Fido's relationship with 4?
Yes. And I don't know if that works anymore, but we could say Fido. And the problem is that you write and it might be able to tell you the relationship.
This ties into the explainable AI in your latest video, which I love, by the way. I'll talk about that. But yes, and I did a stepper one time, which just said, okay, somewhere in my code, there's an intermediate value of 17. I'm not sure where it is, but I got an error message about 17. So I just search if I keep this database of all the intermediate values of a computation, it just searched all the intermediate values. Oh yeah, 17 came up when we were adding 16 plus 1 in the function foobar. And that's
yes.
that ties into your explainable AI, going backwards and forwards. That's really a wonderful search capability.
Yes. One thing I should point out is that this hasn't had nearly the testing it deserves and the experience it deserves. So when I write the code, I say, let's have a sample of a dozen cases. And when those dozen cases start to work, I quit. But that doesn't not mean that all of the cases work. So I'm confident that, and sometimes, so we have a dozen cases that work, and then we say, oh, well, we need this 13th case, and I'll build the 13th case and make it work. And having broken 2 other cases without having noticed, because the testing procedure on this whole system hasn't had the love it needs. How's that for a way to write it?
I'm very into testing. We can talk, a long time about that. Yeah,
exactly. It hasn't had the love it needs. So as we move forward, I want you to understand how that sort of thing works. So in this, what I've talked about so far is we've gotten the dialog box or the agent, which shows you the data content, one that adds things to the data structure, and one that queries the data structure. And what I'd like to show you now is a couple of agents that do some interesting things. And so I'll pull that up and we'll go to a different UKS content here. No, and it is called agent test. And everything's in a different place just to be confusing. But here we have the UKS content. Here we have the same add dialog box and the same query dialog box. And here we have a bunch of agents. And I wrote these specifically so that they would be code identical internally. And so they all live with the same dialog box. And the dialog box, well, let me explain to you how this works by giving an example. Here we have a data structure that has a number of dogs, and 2 of the dogs we know have fur. The remainder of the dogs we don't know. And so if I run the attribute bubbling dialog, the attribute bubbling agent, what happens is it will say, aha, some of these dogs have fur. There is a likelihood that all dogs have fur, and we'll put that up here and we'll give it a somewhat lower confidence because we don't know for sure. And note that these other relationships are still here. And so if I run this agent again, it will increase the confidence. I missed. It increases the confidence that all dogs have fur. So the more often you run the agent, the higher your confidence gets to be. I'm not sure that's a particularly good idea or not, but that's the way it's currently written. And as I wrote this, I decided that originally the single agent deleted these other things. But I realized that there was a much more general case of deleting redundant information, because now if I'm asking for the attributes of say, dog or Fido, Fido has fur with a 90% confidence. What I want to do is now I have a general case of removing redundant information, because this guy gets his information both from Fido, which overrides the dog, and this agent removes redundant relationships. And so if I click that guy, it says it's removed these 2. And when this query runs again, it doesn't delete these, it just reduces their confidence. And so as I run this agent repeatedly, you'll see the confidence goes down until it gets below 50%, and then it's gone. And now Fido only has fur because dogs have fur. Did this make any sense?
Yeah.
Fry's nodding.
Well, yeah, I'm actually looking up some notes I have on BrainSim. I wanted to make another comment, but yeah.
But it's basically clustering. It's basically clustering. This is Michael.
Yeah. Actually, the next dialog box is a clustering dialog box, and this one is sort of doing that and then sort of not doing that. Let's add a few more items, and let's say I missed. Fido is brown. And Bowser is brown. Now in the clustering, what it does is it actually creates a subclass. And I think there have to be 3 members before it creates a subclass. So let's put in Max as well. And I'll go to create a class. And what this has done is it's created a class of brown dogs. And it has made this Bowser, Fido, and Max members of that class. So this is absolutely clustering exact as you would expect it, where the other essentially it's doing, you end up at a similar place with a different data structure. And this is a little less efficient. And so I should be able to run this guy. And now we can see more clearly that dog is brown. It relates to these three dogs, and it has the characteristic of brown. And these other dogs are now just dogs, and we don't know anything about them. Was that clear, Michael? Absolutely. Okay, so attribute bubbling is very closely related to subclassing, but it's that which you call clustering, but it's the same thing. But you have these very modest differences. And I wanted to talk. I'm just going to talk about these, and rather than showing them, one of them is the dialog box is. Well, we'll do that. I'll show you that one in a moment. The next one is a balancing tree, and a shortcoming of things that William ran into is that if you add 1,000 children to a single object, to a single thing, the performance gets really slow because the system just isn't built to work that way. It's built to have relatively small numbers of children. And so what this automatic tree balancer does is if you have lots of children, it clusters the children into arbitrary groups so that the number of children you have on any individual item is much smaller. This one does counts. So if I was, for example, when I'm looking at Bowser, I know that he has a leg. Now Bowser has a leg. And now he moves about and I can see that he has 4 legs. And if I run this agent, it now has the element, it has .4leg, and this is the one that is searchable on the number 4. And so essentially what it does is it goes through the data structure, the UKS of things, and if it finds commonality, like these relationships all have a parent of the type of being 4 and a target of being leg, and so it adds a new relationship with the count. And the reason you do that is that having these 4 individual leg entries is not searchable, but for 4, but having 4 leg entries that has .4 entry is searchable. Now, the question, I've written these in such a way that each one of the agents takes a thing at some point in the code. And so you can say, I want to bubble all the attributes of this thing as appropriate, or I want to remove redundancy from this thing. And so when you think about how this is in your mind, having an agent that goes through and looks at all of the entries in the data structure is exceedingly unlikely, but it is much more likely that the small amount of code that's associated with each agent is actually a part of everything in your mind. And so the thing in your mind that now represents a dog is responsible for doing its own clustering and its own attribute bubbling and its own this. And so this code that does the bubbling exists in millions of cases in your mind, where I've written it once in a for loop because it's easier to write code that way. So in relating these agents to your mind, Another thing that is possible is that some of these agents run when you're asleep. One of the reasons that you do sleep is so that you have a chance for these agents to do their thing without having to conflict with all of the other things that are going on in your mind at the time. So I did want to say, yeah.
I have a burning question here. A couple minutes ago, you talked about dog has .4 .leg. Okay.
Yeah.
Could we also say dog has .2 .front leg?
Sure.
Okay. So we're building up a path with these dots. It's not just one level. We can have an arbitrary length path.
Oh yeah, but do be aware that these things with the dots in them are arbitrary strings, and they are there for your convenience. When you do a search, all of that stuff is ignored.
Oh, it sounds kind of, yeah. Well, yeah, but the question is, does the UKS store this information that a dog has 2 front legs?
Yes. And it creates the children and it does all of the good stuff. But the only thing that's important is that you have the 2 attribute and the legs attribute and the front attribute and the back attribute. And as you search these in parallel, you will always get to the correct result.
Okay, yeah, I'm less concerned about, what is the search syntax and what is the UKS really store. That's the crucial part.
One of my intents is that, well, if you think about your brain and you open up somebody's brain, and by the way, where the place where I did my all of my neurological test instrument work had their 45th corporate reunion, and I went down and visited and saw all of this gear that's from ancient times and from the present and all of this stuff. So it was fascinating to get back and get reconnected to neurons. But as you are, lost my train of thought there. Oh yes, that when you open up somebody's brain, you don't see any labels.
Right.
Therefore, it is reasonable to assume that you have to have a system that can run without labels. And so I look at the labels as being a programmer convenience, so you can figure out what the heck is going on because it only works sometimes as you're building it out. But if you write the code in such a way that it entirely depends on the labels, you're probably working in a different direction than your mind works.
Okay, the labels are like a comment.
Yeah.
Rather than the core data structures.
Exactly. And so the only label that I actually search that's really hard coded in there is that I couldn't figure out a way to not handle the is-a relationship in a special way. And that is because to get things off the ground, you have to say, for example, that has is a relationship type. Well, you can't say is a relationship type without having an is-a to start with.
Yeah,
so there's a bootstrap it somewhere.
That's okay. Okay, so we are allowing has.fur.color brown. Okay.
Yeah.
Now we also could say though dog is brown. Okay. Yeah. And we also want to allow that the has.i.color brown, right? But there's some sense in which if you say a dog is brown, what we're really saying is the predominant color of a dog is brown. And it happens that in dogs, the predominant color would be the color of its fur. So it would be nice to be able to declare that the predominant color of a dog is the same as the dog's fur color. And then when we say dog is brown, what that really means is that the color of the fur is brown.
Yes. These are great ideas. I don't know if the system actually does that at the moment.
I'm guessing
it may all work.
I hypothesize, and humans have this sort of common sense thing in that, yeah, if you say a dog is brown, we're not talking about the eye color, we're talking about the fur color. But for something else, if we're talking about eyes, eye is brown, we're talking about the eye color. So
right. So you kind of have a default that when you say the dog is brown, it defaults to fur.
Like default but I came up with this word predominant because I think that kind of captures the notion here. And then predominant becomes I don't know what it is. It's like a meta attribute or something like that. It's a shorthand. We use it in thinking. It's really easy when we're talking to, we're looking for a dog. Oh, what color is it? It's brown. Oh, okay. What part of it is brown? We all know that we're talking about the fur color, but how do we capture that common sense notion that,
Yeah. We may come back to this in a few minutes, but I wanted to get people's feedback on that video and suggestions for what a next video could be.
I love the video. It's your best yet, Charles. It's really fantastic. I just love it. Now, that said, I have a particular thing that I want to extend it with. Are you ready to hear that now, or I don't want to.
Sure, go ahead.
Okay, it's about the learning section and when you first introduce horse, okay?
Yeah.
So me being a programmer, I want to see like all the way, soup to nuts. So here's what I'm thinking is you got a camera, it takes a picture, and now the system is thinking like, can I learn anything from this picture? Basically, there's this inner loop. Can I learn anything from this picture, right? We got some new input, right? Okay, yeah. So what does the system do? Well, if we were, it maybe looks for the center thing in the picture. And in OpenCV, they have this thing called a blob. It's just like identifies objects that are different from each other. But you don't know anything about the blob other than its perimeter in the picture. Okay, and its location. So we could say, we get a picture, okay, what blob is at the center of the picture, or which of the blobs in the picture have their center closest to the actual center of the frame of the picture? And we can identify a blob. Now we've got a blob, okay, great. Now we start looking around at the characters of this blob. Does it have corners? Does it have lines? All those low-level stuff that you do, right? And you're going to find that it has 4 corners, and, then maybe it looks like a square or something like that. Okay, let's say it's a square. And now we might sort of go through the UKS and say, hey, are there any other squares? Are there any things in the UKS that have attributes whose values are squares? Or we might even say, infer a little bit before that, oh yeah, a square is a shape. Okay, good, we've got a shape. Now let's see if any things have the shape attribute whose value is square. Okay. Mm-hmm. Now, if we have none, we say, okay, we're going to make a new object, and it has a It has all we know about it is its shape is square, and then let's just pretend that's the only thing we know about it. And it's like it's top level. It's is a thing, right? So in your
Right.
in the video, you said it is a question mark, but we'd at least know that it's a thing, right?
Yes. Right.
So we would classify it as a thing. Okay. Now let's say we look a little closer into this blob and we see that it's brown. Okay, cool. Now we want to search for, all right, what in the database has a square and a color. And let's say we find a dog. You know, a dog is roughly a square shape. Okay, just I'm pretending, right?
Yeah.
Okay, now we change that original hypothesis of the is-a-link to dog, right? Because now it seems like that's the most specific thing that has these two attributes.
Mm-hmm.
Okay, and now so this is the way I want you to walk through this horse part of the video, because there was a time when you decided that a horse was not a dog or a cat, and you didn't know what it was, but then there was this bifurcation between whether it's like a totally different thing or it's definitely not a cat. And I got lost in there. It's literally about 4 minutes and 10 seconds into the video or something like that. And that was, I wanted you to connect the dots there with, we're talking about learning here, right? So this is really core.
Exactly. Well, this is one of the great things about peer review is that you have zoomed in directly on the part that we haven't really written yet.
Oh.
And so I don't know for sure that it's going to work.
Okay.
So I was a little, I guess, light on that. And in the event I'm able to make this work, and this is one of the reasons I'm working on the MNIST data structure, is that the MNIST sample set is because it's contained, and we're going to get some new things and some things we don't recognize, and we'll have to cope with things we don't recognize. And what are we going to do with those? And how are we going to adjust what we already know to fit our new information and all of this stuff that really has to go into the answer to that? And the neat thing about that is that when it works, it's a complete replacement for backpropagation.
Yes.
Because we know that humans don't do backpropagation because there is no mechanism in the brain that could possibly work that way, particularly in the time frame that we observe. And yes, ma'am, Heather's raising her hand. I'm saying something wrong.
There is backpropagation.
Oh, yeah. Well, let me rephrase that, but it's something else.
People call it different. They call it different things. So in the brain, you're analyzing, just like computer vision is today, you're analyzing images on multiple scales, and your categorization of the images has multiple scales. So like if you see, like let's say in Fry's example, you have your little robot is taking an image of a dog, and roughly speaking, if you blur the image, its body part looks like a rectangle maybe, and then it has legs coming off of it, and it has, you know, a neck and a head. Okay, so that's shape. So in the first level brain, literally it's actually extrapolating and interpolating all the fur and the hair textures and all that to create that box of the body. And then it's actually doing the same thing for the extensions of that box, the legs and the head and the tail. And so that's a low level categorization. But the high level parts, which are doing the learning like you're trying to do in your model, the high level, they literally have columns of cortex where basically you've learned, and there's neural networks that have strengthened their connections where, you know, you expect to see 4 legs coming off of a rectangular body when it's a dog of a certain, you know, type, right? And so basically that you can categorize that because those columns of neurons have that memory stored. That memory is actually serving as feedback and a primer or predictive coder, depending on the setting, for pulling up your thought that that's a dog from the very rudimentary image that you're looking at. So it is kind of a backprop in a sense.
Well, certainly.
Where's the back propagation?
Huh?
Where's the back propagation?
Well, just the back propagation is only in the sense that you actually get literal neural circuit feedback, which in some respects serves kind of like a neural network backprop.
You know, one of the things that I'd really love to do is to, you see a small corner of an image.
Yeah.
And you match that and against and you get a number of different results. And now you're only searching amongst those results as you search for what this thing actually is. Yeah. And so from this, it's the case of you see what you expect to see, and the totally unexpected is very difficult to see.
Oh yeah, that's a whole other level.
And
there's another aspect too of that same thing, is that perspective. Every object, every visual object that we have, and to some extent other modalities, but basically every visual object you have takes on multiple two-dimensional shapes depending on how you're capturing the image.
Yep.
Because it's a three-dimensional object. And so your brain actually has capacity to store. It literally has columns that will store images. It will store your memory of what a head looks like with its eyes, nose, and mouth, and to categorize it. And it will store it in different perspectives. And literally, when you see movement, it's moving activity across those columns, you know? So I'm just saying that those things exist, is that there is a hardcore memory for all the different perspectives of a three-dimensional object. And I don't know in computer vision how they're doing that right now. I should know that.
Well, that is excellent. And one of the things that of course, after I get two-dimensional image recognition working, is obviously you have to project this into 3 dimensions.
Yeah.
And that's something we did in the previous revision of this software, and we did it in a highly numerical way. And we are pretty sure that your brain doesn't do sines and cosines internally. And it, what it doesn't do mathematically, it makes up for in volume. But do you have any idea how many different angular images you store in your brain?
I don't know exactly, because but like Tanaka was an old paper where they showed that you literally stored at least 5 columns of perspectives of heads. So that would be kind of like 5 perspectives,
Oh, that is a good number to think about. So what I'm hearing is more than 3 and less than 100.
Yeah, exactly. And I mean, in audition, it's going to be slightly different, because if you have a single microphone or even 2 microphones on your robot, because of physics, you have ambiguities about, sounds that come from front and back. There's a little bit of ambiguity, but that's okay. So I'm saying the rules will be slightly different when you start to cast the same question in the auditory system.
Yeah.
So, but I think vision is the first part to start. I think you're doing right with that.
Yeah. Backing up about 12 squares, we were talking about things that we need to add to the video or put in the next video, which is much more likely.
Yeah.
learning is certainly a possibility. My experience has been that when I actually sit down and start showing how the software works, the audience vanishes.
Really?
And yeah, and the more I talk about here's how your mind, the more I talk about code, the more people don't pay attention.
Really?
Maybe I need a different audience. But and I tell you, it's a lot more fun to make videos that 1,000 people watch than videos that 100 people watch or that 10 people watch.
Well, but ultimately, Charles, the important thing is not the actual videos. It's the conceptual stuff of getting this model right.
Exactly.
That's where the big progress is here. And I would be delighted to sit down with you and brainstorm through this learning stuff that I just described, because it wasn't clear to me from the video whether that was stuff that was undone or simply stuff that you didn't explain well. Right?
Yeah.
I had no idea, which I assumed you knew.
You mean I covered for that really well.
And you just didn't explain it thoroughly because you didn't have time. I mean, a video is only going to be 15 minutes long, so
yeah. But I mean, as we produce a system that learns, and of course, Michael's suggestion from I think last time or the time before was that a key feature is unsupervised learning, that if you simply don't recognize stuff, you stash it away somewhere as something to be learned about later as you learn more and more details. So the child knows what a cat is long before they learn the word for the cat.
But I didn't like to stash it away somewhere. You had big question marks, and that was, well, what the hell is this? No, we at least know it's a thing, right?
Yeah,
as we learn more, now it's an animal. Oh, which kind of animal it is? It's a dog. Oh, which kind of dog? It's a collie. So it's just a refinement of our knowledge, not a, gee, we don't know what the heck this thing is. No, if you
absolutely
really have absolutely no idea what something is, you'd probably just forget about it.
So I have a slightly different approach, a different take on things, because I'm trying to do developmental robotics and to, come about things tabula rasa. So I'm working on a new video, and hopefully it'll be out soon. And part of it is using different associative memories. And you stash stuff in these different associative memories, basically. And initially you have a perception that comes in, and that perception gets decomposed into features. And then that perception and those features get stashed in an associative memory so that the perception can be retrieved by those features. And then you build on that. And so, building on that gets into George Lakoff's work and other people's work. So it's pretty interesting.
Mm-hmm. Well, one of the things that will be unique about our learning process is that is Fry glossed over here is that what we're doing as we learn more about something is we're changing where it fits into the hierarchy of things we know about. And so it's not just that we've got something and we're adding attributes to it. As we learn more about it, we're learning that it's a horse or a mammal or an animal or something like that. And I haven't pursued this at all, and I cut it out of the video, that essentially all physical objects inherit from a master physical object thing that grants it mass and gravity and inertia and the fundamentals of physics that every object shares.
And my only question, because I'm coming at it from the other way, I'm building all of these things up instead of having them defined a priori. Why couldn't those be assembled as opposed to, outright designed initially?
Oh, I absolutely agree with you that these are things that you learn by example. The child learns that things fall down. I can't imagine that that instinctively that things fall down. This is unlikely.
I want to form a bridge between what Michael said and what Charles has said. So Charles said, "Oh, we'll just stash something anywhere," and I said, "Oh, I don't like that." But actually, Michael has a system where you do just store it anywhere. We're just like one giant linear database of attributes and associative memory. Okay, good, that works. Now what I'm thinking of, as you sleep, as Charles was mentioning, we run over this associative memory, and we notice, oh, these things have the same attributes as those things. Oh, we have 4 things that all have, brown fur and stuff. So let's kind of cluster them together and make a category. And now we're moving stuff from or I don't want to lose Michael's associative memory. Let's always keep that, but redundantly, we're pulling things out of there and putting it into Charles, and now we've got a category of a dog or things that are brown or whatever.
Multiple associative memories, absolutely.
Michael, are you just saying that the UKS is a multiple associative memory?
No, I didn't say that the UKS is. I'm saying that the process that I'd like to describe has multiple associative memories. So you have perceptual memory for the features joining to the percepts, and then you have other associative memories as well.
Wait, I'll add something.
Go ahead.
Hey, and Michael, what's your last name? First of all, Mike Miller. And you're going to have a YouTube video on your memory stuff. You have your own YouTube channel?
Yeah, he's Subthought.
Yeah,
Subthought, that is your YouTube?
Well, no, it's called @Cognitive Architectures.
Oh, really?
On YouTube, if you look for @Cognitive Architectures, one word, you'll see it.
Okay, sure. Anyway, I was going to say, conceptually, what you're saying, in some cases, is there's a hierarchy for associative memory, right? It's kind of very complicated in the brain because your brain is highly parallel, but it's also highly hierarchical in how it builds up memories. And so the concept could be that as you're building memories, that you're conceptualizing it, a mammal as a dog or a horse, right? Then you're going to potentially have this ability to have a hierarchy for, first, like you said, you're learning the parts of this animal. And then at some point, you're going to build a memory in a category that's not unlike the UKS. I don't know. I would have to think more on that, right? But it's not unlike it in terms of saying that it has an object has a memory in terms of multiple things, like its attributes, but also things that it does physically. And so you build up a hierarchy in different parts of your brain to do that. But you're right. It's a process. You have to build it, right? The memory.
Absolutely, I agree. Yeah.
Okay, so to kind of follow through my process of building this hierarchy, we've got Michael's associative memory, just a flat, one-dimensional array of all these things that have these attributes. You have something that's looking over and says, hey, I've got a bunch of things that are brown and have 4 feet and tails. And now I want to make a category, but I don't have a name for that category. But we could sort of make up a name that says things that have 4 feet and brown and tails, right? And later we might figure out as a dog, but we're not worried about that. And then those things that
Fry, you don't need any names. Just make the category. That's it.
Oh, okay,
Just
fine.
make the category.
Now
Forget about the labels.
Okay, now we have Rover, let's say, and Rover exists both in this linear, pure, one universal associative memory and in the hierarchy of things that have tails and brown and 4 feet, right? And Rover might also exist in some another category of pets. Okay, just that.
Absolutely.
So when we have that, Heather, you're talking about hierarchies, but I don't know if it's fair to say that a node in a hierarchy can exist in 2 different places of the hierarchy. Is that still a hierarchy, or is that a different data structure?
It can exist in 2 different places 100%. And yes, the hierarchy, oftentimes it plays out in real life with temporal dynamics, temporal and spatial dynamics, right? So that's another level of complexity, right? But nonetheless, you can have it represented literally simultaneously across the hierarchy.
Okay, and
we probably call it a we probably call it a heterarchy instead of a hierarchy.
Yeah, well, that's a good one. But the bottom line is that we also have behaviors. So you could have wait. Before we go to a little kid going around and pretending to be a kitty cat, going meow, 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 and crawling on all 4 legs, but it's a human, right? So a young child would actually quite literally say, "You're being a kitty cat." And so our robot would not necessarily do that unless we had a specific sequence of events that kind of characterize the behavior. Right?
That's called a symbolism.
Yes.
And we can I have an idea on all of that as well. But that is called a symbolism. When a symbolism has 2 parts, a signifier and a signified. The signifier represents something that's present in the moment. The signified represents something that may be absent, but is a substitution for the present item. So yeah, when a child says, "I am a cat," the child is the signifier and cat is the signified.
Yes, I like that.
So Heather, if you get into computer data structures, normally I think a hierarchy means single inheritance. You have one parent.
Yes, when you're being explicit. Yes.
When Michael's talking about heterarchy, and when you're talking about a node existing in 2 different places, that means a node can have 2 parents. So it's a heterarchy, and there's all different kinds of reasoning that you do with hierarchies and heterarchies. They really matter about how you're thinking about comparing objects, all kinds of.
I agree with the code for sure, but I also agree that there is still a fundamental hierarchy because, like the crude shapes that you might categorize at a first level it's a low level. And then when you have enough information to say that is definitely a kitty cat, then that's a higher level. You have reached the levels where it takes a long time to train those in your brain, actually. But, basically you train them in your brain. Eventually you have actually real memory spots for those categories, the high level.
Okay, I want to be careful here.
Yeah.
In a heterarchy, you can have a subset of the heterarchy be a hierarchy.
Yes.
I mean, heterarchy means one or more parents, not more than one parent. So if you have only one parent and everything below this one parent also only has one parent, then we have a subset of this that is a hierarchy. That's okay. Yeah, but in the larger sense, as we zoom out, we've got a heterarchy because Rover is both a cat, a pet, and a dog.
Yeah, ish. Yes. But the bottom line is that, you know, that, I mean, brains actually have both heterarchy and hierarchy, because when you're doing executive control functions where you're trying to manipulate what's going on in the room, like you want to grab the kitty, you actually have to basically recognize that the kitty's coming in the room and what he's doing, and be prepared to do what you want to do to pick him up. And that actually means that you have to have the incoming information, seeing him move around in 3 dimensions. Oh, that's that kitty. And then at the same time, have the predictive coding and say, I think that's a kitty and I'm going to grab it. And so those, yes, those are heterarchies of a sort, but they require a hierarchical organization to some extent.
Let me put it a different way. A hierarchy is a subset of heterarchy.
Of course. Yeah. But when you were talking earlier, Charles was talking about trees. Like in coding, you're doing trees. There's almost an obligatory.
A tree means hierarchy.
Yeah.
Yes, that's what I'm saying. So yeah. I'm just saying that there needs to be a thought about parallel exchange of information in addition to.
Right. And I should say that the UKS is a hierarchy, but all of the explanations are more convenient in looking as a hierarchy. It's easier to explain.
Enough. Yeah. I might even say it's UKS is a graph, and let's just
absolutely
throw out all constraints, because pretty much you can connect anything to anything.